looking forward to this discussion on this panel, talking about where we're going in California with respect to defining a more than smart distribution system. The panelists here, Ryan Hanley on my furthest right, is Director of Engineering Solutions or Grid Engineering Solutions at Solar City. Manho Yeung is Senior Director of System Planning and Reliability at PG&E. Next to him is Dave Geier, Vice President of System Engineering at San Diego Gas and Electric. And to my immediate right is Erik Takayesu, Director of Electric System Planning at SoCal Edison. All of these guys have been actively involved in an effort that, as we've talked about already this morning, that started over a year ago, looking at what we need to think about differently in terms of an integrated grid, as EPRI calls it, what we've called here in California more than smart. So how do we take what the good work that's been going on, and how do we evolve this to be able to accomplish the goals, both from a climate change and more specifically the distributed energy resource integration that we're trying to accomplish here in the state of California. So with that, I'm really pleased to have them all here as part of this panel. We'll start with some opening remarks and some slides that each of them have to describe what we think the current evolution of the distribution system needs to look like as we move forward, as we define what more than smart is with respect to the grid. Excuse me, and we'll start with Dave Geier.
Thanks, Paul. Good morning, and thank you for having us today. Get the next slide, please. This is going to be sort of interesting to look over my shoulder the whole time here. But I think it's really interesting this morning, the few hours we've had already, to sort of see how we get lots of different opinions, but there's a lot of common thoughts here that people are really getting close to the same page. So I really think that's great for our state, and it really shows that we are a leader here. I'll talk a little about the SDG&E's vision for the distribution system of the future. We believe that we are consistent with state goals, and probably the biggest sort of concept we have is open access. Okay, and we believe that we should be able to hook up DER anytime, anywhere for those that have. And Peter used the term energy only. Okay, that could be the customers of the PV panels today. They're just out there for energy, saving their money on their bill or whatever. When we get down to getting capacity and reliability benefits, then it needs to be sort of in the right place, the right time, the right size, and I think we can all work together on that. So I think there's a lot of opportunities there. We talk a lot about electric vehicles. Mary just talked about that. We want a distribution system that will allow us to hook up as many electric vehicles as possible out there. Actually, that's the goal, right? We want to have a distribution system with no limitations. That doesn't come easily, but we can do that. And then we talk a little bit about, in a couple of different places, about getting the rate structure right. That's hugely important. In fact, we feel that to have a plug-and-play environment in the future, we need to get the rate structures right. And really, I would go as far as to say, really, our open access policy is sort of consistent upon that. Getting the right tariffs, making sure that everybody is paying their share if they're using the distribution system, and just getting all those cross-subsidies cleaned up. And I think we can definitely do that. Next slide, please. So this slide I sort of call my guardrail slide, right? And it's really not too complicated. I'm an engineer too, but you sort of look at this. We should make investments that are smart, that improve reliability, resiliency, decrease greenhouse gas, enable customer choice, be cost effective, and benefit all the ratepayers, right? Those are all the good things. We can make investments on the other side. They're all bad, okay? And I just sort of think these are the guardrails going forward. Next slide, please. We have over 300 megawatts of solar PV in San Diego. We've put a process together where we actually can expedite the installation process. Works really well. But we're also spending $2 million a year to get these installed, right? And all the ratepayers, again, are paying for that. So we need to sort of get that right. One thing we think is that the solar PV should have similar characteristics as any other generator out there, right? And that means from an intermittency point of view, from a volt-var perspective, and we're not quite there yet, but a lot of talk about smart inverters. We're going to get there with smart inverters. I know that. and that's really a good step. But then also, we talked this morning about integrating storage, and that can be a great thing also. Next slide. I think we've all seen this, that if you look at residential circuits, and we have a lot of residential circuits in San Diego, solar doesn't line up with that right now, right? And that's really an opportunity to match up storage, both distribution system storage and customer storage. The commercial profile is a lot better, actually, so there's another opportunity. Next slide, please. Let's talk about storage a little bit. Trying to get the demands lined up, smoothing out the intermittency, all really advantages of storage. And we think that I think if you start coupling storage with the generation, it's the real winner right there. We have a couple megawatts already of batteries out there. We're in the process of putting another 5 out. The chart there just shows, we have our target of the 165 megawatts. We will get there. We got a process in place, and we're moving forward. Next slide, please. This is a real customer. This is the San Diego Zoo, and so we all know about the San Diego Zoo. The important lines here are the green line and the blue line. The green line is sort of the raw PV out there, and the blue line is you integrate with the red, which is the batteries, and look how smooth that is, okay? We know this can work, and we know just getting the control systems in place is hugely important, but the combination can take all this intermittency we've been talking about and really clean that up. Next slide, please. So again, our vision here is that we want to integrate as many electric vehicles as possible with having minimal impact on the distribution system. We all know that if you do it at the wrong time, we're going to be having a lot of impact on distribution transformers. We don't want that to happen, services, things of that nature. And we want them charging in off-peak hours. That is huge, and what's really different and what you have to sort of get your head around is the whole duck curve, right? Those off-peak hours may be in the middle of the day in the future, right? So we really need to think about that. But again, I look at that as an opportunity, not a problem. So the next slide, we talk a lot about cost for electric vehicles. This is just a comparison. If you look at comparing it to the gasoline, which is on the far right, to go 100 miles, and this is what the average GPA car costs you $15. When we charge is hugely important, not only from a grid perspective, but getting it back to the customer. If you look at, we have an EV time of use rate in place. Right now it's a whole house, or we had some experimental rates. It's about 1/3 of the cost of charging or of driving a car with gasoline. So here's the win-win, right? We can reduce cost, and if you do it at the right time, it can help the distribution system. Next slide, please. So, it's a lot of complicated things out there. We already talked about this morning. We can leverage the new AMI systems we have across the state of California, a huge amount of data. We have a new GIS system in place, and we're capturing where all the PV is, where all the solar is. All those things will help. We're in the process of developing a new DMS system, which is a distribution management system. That will bring in a lot of the data, help us with that data. And then the DERMS is a control system for all this resource out there. Those are the things that are in development, and I think there's probably going to be a joint development in the end. So in conclusion, open access, we believe that can happen. Get the rates right, rates right for the customers. That would be really good. If it's not energy only, let's put it out everywhere we can. If it wants more distribution capacity benefits, it's got to be in the right time, and really get as many electric vehicles out there as possible. So we are very supportive of this state policy, and we just have a lot of work to do there. Thank you.
Thanks, Dave. Brian?
All right, thank you. I'll start and say thank you to Paul, to Tony, and also the 3 utilities here. We've been working collaboratively for several months, and it's been a nice opportunity. And if you don't mind, I'll actually maybe speak from up here. Our marketing team did a great job on our transitions on our slides, and it might be unwieldy. Great, so before we dive into what integration of DER looks like or what the grid looks like, we'd like to frame it with a discussion of why do we even care about integrating these assets. So it might be self-evident that the grid we're talking about in the future, what it can be is clean, obviously, but we also think it can be, it needs to be resilient and affordable. And the great thing with a distributed system is that it's not as just keeping the same level of cleanliness, resiliency, and affordability, but it can be an improvement on all of these. You get obviously the clean assets that are down at the individual houses and customers. As importantly though, individual homes, you can improve the resiliency with DER assets, batteries that back up critical power. You can do the same thing for communities, neighborhoods, and even feeders, referencing Susan Kennedy's microgrid discussion before. All these are improvements, we think, on what the grid currently does, and something that is a great thing to embrace. And the same thing with affordability. With the cost curves coming down aggressively on all these assets, there's also another component in this industry that drives affordability, and it's taking bets on these investments. A decentralized network inherently allows you to make smaller bets distributed across the system, and you're making inherently less large bets that could go wrong. No one can predict what's going to happen in 20 years. We think there's a key argument for affordability in these assets. And I think you're all familiar, we talked in detail what these assets are. The key question is not necessarily how to optimize every single one of these. It's not the key question I think the utilities are considering. It's more of how do we start to optimize them collectively to serve as an asset for the grid. And we obviously think that a large number of homes, commercial customers as well as industrial customers, if they have these portfolios of assets, it then opens up 3 different ways that you can use this asset. We refer to this internally at Solar City as kind of the triple use asset. First, you have the benefits to the individual customer. Instead of just having solar on a roof, you can have solar plus battery plus load management. You start to optimize all these assets together to either flatten the load curve, deliver value to the customer for whatever they need locally. On top of that, there's assets available for the second use, distribution assets. We have a lot of great discussion with the utilities now on how we aggregate thousands of these customers on one feeder and make them available to, say, defer substation investments, or in this example, cut peak load. One of the exciting things that we're doing in our simulations now is a little bit surprising to us that the cost of these aggregated solutions are on parity, and if not, in many situations, cheaper than they are for your typical substation upgrades. And we think that's kind of a new thought. These are available now, and with investing in the platform to be able to control them, they become reliable and alternatives to invest in substation deferrals right now. And the third is being able to use these for the system. Dave mentioned the duct chart. We all know it very well. There's a lot, in this example, you can use it for ramping capability on that duct chart, but there's a whole host of assets or a whole host of use cases that those assets can be used for. And while right now a lot of the focus technically is let's make sure these assets can perform one of these use cases, totally get it. Long term, we think that there's a way to prioritize each one of these assets so that it serves the customer need initially. It's there for the utility when they really need it for substation deferrals or any kind of capacity challenges that they might have on 5 days or 10 days of the year, but not all the other days. And then you also have it when you have excess resources or an opportunity in the wholesale markets to engage and provide a resource for the entire market. And so with those benefits basically comes a need for what the platform needs to look like. Going back to the inherent value in a distributed network, you have these smaller bets that you can use in very flexible ways. They're being designed by folks like Solar City, all these other folks that are delivering these platforms to be inherently flexible. There's no way that we can guess today what the need is for. So we don't necessarily want to design a platform where our assets can only serve one utility function. If we can update them, things like remote firmware upgrades, whatever you have, we can respond to the utility needs, to the grid needs in the future. And we think that's a capability that doesn't belong necessarily to, or is not as easily attributable to large assets. And the same thing that we're working on, I would venture to say the utilities are working on the same thing. Flexibility in their control platforms so that they can harness these assets and use them for a grid that will be changing dramatically in the next 20 years. So looking forward to getting a bit more detail on those topics, and thanks for the opportunity.
Thank you, Ryan. Erik?
Okay, thank you. And first of all, I really appreciate the opportunity to be part of this panel. Thank you, Paul and Tony, for putting this together. And I did write a note to myself that Ryan's going to be in charge of my slides going forward into the future. Nice job. Anyways, so my presentation is really going to kind of run through a story, really just going to sort of level set where we are with our current grid, where we've been with smart grid deployment, and where we think we need to go going into the future to support this transformative change. So if you go to the next slide. Okay. So if you look at our current grid, I'm really showing 2 illustrative examples. The example on top is our bulk power transmission system, and below that is what could be characterized as a very typical overhead distribution circuit. Now, the bulk power system is considered a network system in that the power flow on it is based on a number of different things. such as the physical characteristics of the system itself, generation, transmission interconnections for import and export, and the variations on the distribution system. So the issues around things like two-way power flow don't pose the same challenges as what you would normally see on a distribution system, which I'm showing below. So this is considered, like at Edison, it's predominantly a radial system, meaning that it has one source, which is a substation, and flows directly out to customers, and I think we've all heard that quite a bit. But one thing that we really integrate as part of our planning process and our operations is the idea that all of our distribution feeders have connections to other circuits, multiple connections. And so they do get reconfigured quite often. We reconfigure feeders for things like taking equipment out for maintenance, emergency restoration, and load balancing. And so when we think about things like two-way power flow and reverse power flow, insignificant amounts is where we consider the issues around things like protection and voltage regulation. And interestingly enough, really between both the transmission and distribution system, particularly at Edison, location is very important when we think about things like how much distributed energy resources can be accommodated on the grid. We deal with things like transmission, congestion on the transmission system. We look at the differences between rural and urban circuits. I think there was a comment made this morning about there were differences in areas between the coast and the city. And so different parts of our grid are constructed differently, and they're constructed that way primarily to serve the load-dense pockets that we have within our territory. So go to the next slide. So over the last few years, we've had smart grid deployment plans, and they really did set forth a really good baseline for technology deployment. So we have pilot applications for things like storage. We're showcasing other technologies that I think will help us moving forward. But as I think about where we need to go to support some of a seamless integration or node-friendly environment, there's some broader portfolio of transformative changes that I think we ought to consider, especially over the long term. So if you go to the next slide, please. So the way I kind of group this when I think about modernization as opposed to smart grid, and this is kind of going sort of the beyond the smart and the more than smart, is we kind of think about grouping these into three primary focus areas. The first is in the area of planning. Our current distribution planning processes are primarily driven by the need for reliability, also driven by the need to ensure that we have adequate capacity. So one of the things that we're having to consider now is how do we relook at that process in order to determine how do you quantify the ability for a system to handle generation on the distribution system as opposed to strictly the peak load that we used to serve. So low profiles and other things become very important. The second thing is that the technologies around integrating within the planning process have to be considered in terms of its unique characteristics. So one of the things we're thinking about, and I think Ryan, you referred to this in your presentation, is that when we think about smoothing out the low profile and using distributed resources as grid assets, we have to think about the combination of technologies that can work together in a coordinated fashion. So if we have solar output PV that's intermittent, but that could be smoothed out with storage, low profiles can be leveraged with demand response, somehow the planning process needs to encourage our ability to have the technology and the processes and tools to support drawing these equivalents between what the grid is capable of doing through its normal traditional investments and what these sort of coordinated integration of these resources can do. The second major area of focus is operations. And it really, in my mind, is tied together with reliability because the system would become more complex. Our operators would require better situational awareness of what's going on the grid, not only to understand the current state, but to make decisions. We talk about these reconfigurations and things that have to be normally done on the grid. Having that situational awareness is going to be important because our operators work in centralized locations. They're not situated in every substation. So we do have to deploy things like better monitoring sensors on the distribution system, communication and control abilities that can help them manage the grid in ways that they haven't had before. So we're looking at things like what is the potential bandwidth and latency requirements that we're going to need to evolve our communication systems now, as opposed to the automation systems that we used to have when all we really needed to know was whether the voltage was on or off to do automated switching. So to monitor and measure these two-way power flows, what kind of sensors can help us do that? And really even the current apparatus that we have on the grid, the way our automated switches work and the way our automated capacitors work, they're generally today single-phase devices that are looking for interaction on one of the three phases. So how do we convert those to three-phase devices so we can leverage the same equipment but to have additional capabilities? The third group for us is around optimization. And we think that that's an important aspect when we think about planning and operations to manage costs. That allows us to dive deeper into understanding the cost benefit of distributed resources across the overall grid between the distribution and transmission systems. You know, what does it take for us to defer capacity upgrades? Do the technologies that we're deploying, how do they improve safety and reliability? So we ought to think about if we're going to have to modify our communication and devices that would need to be advanced, we might as well consider those much larger improvements to things like public safety and reliability that weren't available to a radial distribution system before. So as we look to the grid of the future, I think this transformation has started, and like Dave said in his opening remarks, it is very interesting to see how I do think there is some convergence around what needs to happen on the grid. Now, the grid, in my mind, has always been an enabler of technology. You know, throughout the 20th century, all the things that we have and all the luxuries that we have today are enabled by the grid. And we believe that by having these transformative changes, that enablement of technology and innovation ought to continue to occur in a way that meets our greenhouse gas goals. So, thank you.
Thanks, Erik. Manho?
Good morning. Actually, I guess it's almost afternoon. With the last thing starting with why most of the time I'm the last one to speak. Anyway, my presentation actually is very similar to Erik's. Can we go to the second page? And just a quick description of the PG&E distribution system as a company. We cover a pretty large geographical area, 70,000 square miles, more than 5 million of customers. And our peak demand is in the 22,000 megawatt range. Over 50% of our electric supply is from non-greenhouse gas, which is something that we're pretty proud of. From an RPS standpoint, for this year, we're getting to the 27-28%. The rest of the non-GXG are the large hydro and nuclear generation. Quickly on the distribution grid, we have more than 3,000 distribution circuits or feeders, and 142,000 miles of distribution lines, and we have one of the biggest distribution system in the country, and 1.1 million line transformers and conductors and transformers are the basic workhorse of the distribution system, so to speak. And we have a number of fuses, reclosers, and things like that. And actually, one of the things that Tony asked us to do is to tell a joke, because some of the things that we talk about are pretty dense, so to speak. Not that we are, but the things are. And I'm an engineer, so I do pretty well on problem solving, but not really on jokes. So, but I'm glad that we're talking about this before lunch, not after lunch. So turning to the next page, we have been seeing, just like a lot of the observation, that we have been seeing a rapid growth of distributed generation in the system. And I really like this chart to show in the early 2000s, we hardly have any in the distribution system, and just looking at the exponential growth over the years. This is just amazing. At this point, we have a little bit more than 1,600 megawatt on the system. And I have some statistics there that we have more than 130,000 customers that have rooftop installation, which is just amazing as compared to a few years ago. And we also show some of the statistics on the distribution feeders. We have more than 50 circuits that have penetration more than 100% or close to 100%. The way we define that is looking at the amount of install capacity as a percentage of the peak demand. Some other people look at it differently. For example, my understanding is that Hawaii look at it as comparing with the daytime minimum demand of the feeder. So you can kind of multiply the numbers that I here by 2 to do the translation. And one of the key things that we have also been seeing is rooftop solar. It's just amazing in terms of the adoption, particularly in the past couple of years. Nowadays, we're seeing more than 4,000 applications per month. I guess one way to think about it, as engineers, we have PG&E. One of the key learning that we have in looking at this growth is to listen to the customers. 4 or 5 years ago, we are pretty bad in terms of connecting customers that have rooftops. The regulation is we need to do it within 30 days. 4 or 5 years ago, we were averaging about 15, 16, 20 days. And this is something that we have been really focusing on in the past years, and focusing on process improvement, focusing on using technology, using the internet, electronic signatures, and things like that. And we are at a point that on average we have 4 days. 4 days from an application is completed to PG&E providing the permission for the customer to actually connecting to the grid. We're looking at continue to improve on that. We're looking at moving down to 3 days and down to 2 days into that range. One of the other observations is that even though with 1,600 megawatt of DG, so far we have not been really seeing a great need for a lot of upgrades into the distribution grid. So but on the other hand, what is missing on this page is electric vehicles, energy storage, and as well as the adoption rate on rooftop solar is expected to be a lot more moving forward. It's going to get to the point that we will be seeing needs to upgrade the system to accommodate that. Okay. Next page, please. So this is another kind of geeky look at the system. Is what we call a grid of things, similar to I guess the Internet of Things in a way. And we kind of look at this as the three key things that we're looking at, and I like colors. Is red, yellow, and green. Kind of looking at things from a safety perspective. We must ensure that the system is safe for the general public and also for workforce safety. And the green portion is on voltage regulation. With the multiple devices there, we need to make sure that the system is regulated in such a way that we provide quality of service, so that the voltage is not too high that would burn out PCs or motors, or the voltage is not high enough that it doesn't have enough power to do work on the system. And the yellow portion is on the conductors and transformers. As I mentioned before, we have a lot of those, and it really is a workhorse of the system. We have been talking about two-way flows for quite some time now. From the transformers and conductor perspective, it doesn't really matter to them. They do equally well whether power is going from left to right or right to left. Another point I just want to point out is that the other design aspect of our system is that we have main line and also we have the tap line. The main line is typically where we have a bigger size conductor, and so that have to be more robust, more capability to it. When we get to the tap line, which are the next level of the distribution facility to serve a smaller amount of customers, they tend to be smaller size in nature, and in a way, that's where some of the upgrades may be needed on the tap line as well as the main line to make sure that the main line is big enough so that you don't see the voltage fluctuation, as well as having enough capability to serve the customers. And actually, one other thing is on this page is there are certain things that are missing here. What is missing here is the customer portion of the grid, depending on, there was an earlier discussion on where the grid start or where the grid ends. So what is missing on this page is that particularly smart inverter. Smart inverter from our perspective is a key control device that is emergent as a critical component that we need to consider and integrate into the system. Last page, it's just to share some of the programs and initiatives that at PG&E we are doing to make the grid to be more intelligent, robust, and affordable for our customers. And the first one is smart meters. A lot of us have talked about that. With the smart meters, it provides a lot more information in terms of customer demand and what the customer needs are, so that we can plan the system accordingly. The next 3 or 4 items on SCADA, sensors, VOVA, optimization, and smart inverters are control devices that as a utility, PG&E is starting to understand more, as well as being able to use them more effectively, more intelligently to serve our customers. The next one is on FISR, which is for location, isolation, and service restoration. In a way, it is a feeder automation that PG&E have been able to install into the system over the past few years. About 25% of our system has this technology. Basically, it is able to detect where the problem is if there's an outage and quickly isolate the problem, as well as making connection to an adjacent circuit. Erik talked about the connectivity, so we have certain capability and be able to swap over, so to speak, to an adjacent circuit to quickly restore customers. Next item is on standardization. That is helping us to provide the margin that we need for the future. In the past, it's more focusing on, so to speak, of engineering economics to figure out what exactly do we need and design a system to serve that. The standardization help us to think about more globally, as well as kind of really focusing on the type of material that we carry from inventory, that also helping on the maintenance, on reducing maintenance and operational cost. The last item is location. One of the things that we have not really been doing a great job in the past is to provide information to the customers. So the location aspect of it is critical because by placing DER in the right location, that would be able to solve a lot of problems in providing additional values to the grid. Whether it is how do we optimize the different resources, or to compare that with upgrades or work that we need to do to the system in terms of to see if there's any synergy between them and be able to capture the benefits. Another item is on duration, on when resources are going to be there, which is another consideration that we really need to look at moving forward. Thank you.
Thank you, Manho. So, I want to open up to questions for the panel, and maybe I'll start with an open question, but please, if you have a question, tee up. Each of you have talked about a number of elements related to what we talked about in the Merwin Smart paper around the cycle, the life cycle around planning, then design, build, and operations. And there were elements in there in terms of both the opportunities that we talked about, but there were also some challenges around engineering or new technologies that could be real enablers for how we both do the planning, design, build, and operate. And maybe if I could ask each of you to sort of highlight what you think are both some of the near-term engineering challenges that we could focus on, as well as what you think are some of these important enabling technologies. I mean, certainly storage, we all talked about that, but maybe beyond storage that we haven't emphasized so far. Maybe Ryan?
Sure. Yeah, so for engineering challenges, our perspective is the biggest challenge of the grid right now is its utilization. You talk about the grid, and if it were a manufacturing plant, the utilization would be somewhere between 50 and 60%. You'd be hard-pressed to look at any other industry in the world and find utilization so low. And overcoming that, getting more out of the assets that are in the grid already, is the answer to driving down cost. These cost curves for individual technologies will drop. Interconnection challenges themselves will be overcome. You can look to Hawaii, for example, to see on any individual feeders. Commissioner Akiba might know this better than anybody. We're overcoming those challenges to actually connecting DER to the grid. That still, however, doesn't address that we're living in a world where overall our assets are underutilized. And you start to talk about the role of engineering design criteria and what is keeping that utilization down. Most of the design right now happens on an annual basis. You're taking a look at your data, you find the maximum capacity that asset can go in, and there's a constraint on that installation that comes from probably 5 to 10 days, when there's peak power or peak power demands. The rest of the 355 days, that asset is underutilized, or you have other parts on that feeder that you could install more that could operate for 355 days of the year. So it leads into this discussion of dynamic, starting with dynamic engineering constraints. If you could change every day and really optimize that grid every day, you could get more out of the assets you have. It then flows quickly into, well, there's a lot of supporting technology to do that. These guys need a lot of data to be able to change every day. They need a lot of control systems. And it opens the world up for, how do you do that control? And the last thing I would say is, specifically with products, it might be helpful to leapfrog our thought of control right now. If we take our existing playbook, we'll extend centralized control down to every asset and have direct control. And that would solve it, I think, for an operator. However, the investment to roll out a dedicated control system to every device, and those devices are changing every year, we would argue is incredibly cost prohibitive. If there's a way to coordinate all of these customer-owned assets in a way that still delivers the performance that these gentlemen need to operate the grid, we think there's a marriage there that starts to bring the whole utilization up, as well as keep the cost of investment down. Thanks.
Sure. I definitely agree with the comment about utilization, because because right now the system is passive in nature, that the system needs to be there to serve the customer whenever the customer turn off the light or go to run the dryers, and so that's the issue on how do we balance or how do we change the energy consumption in such a way that you have a higher utilization. And I think on top of that, it's really what is the future holds for us from a scenario-based planning standpoint. I mentioned about for PG&E we see 8% on DG in the system. What happened when they get to 25%, and how is the storage going to tag along or to be integrating into that? So that is kind of the second things that is on our mind. The third area is the control. Smart inverter holds a lot of promise from a control and managing the overall system. It would be really great to have that to be to autonomously regulating the system without having to have a big control system to be really in place.
Dave?
From my perspective, it's all about data, right? And you think about all the things that Ryan and Manho talk about, but the two systems I think we need are this distribution management system and the distributed energy management system. I think the key word there is management, not control, right? Because I think we're going to have all this distributed control. It's coming back, but we need to manage that grid going forward. So, and all that comes back to data. The other big piece of data, and we've talked about this, is sort of the price signals to customers, the whole rate reform. We're living in California. We have antiquated rates that really have come from an energy crisis, 13, 14 years ago. A lot of work going on that. If you get that right, give the customers the right price signals, we will get integration both of electric vehicles, more PV, using it for more things to get better utilization. So it's all about data and the big management systems of that data.
Yeah, so I agree with the data comments as well. For us, we're thinking a lot about the communication systems and the security of those communication systems that are going to be required to bring in all this information to be used for various things. So I think that the communication system is one aspect, but I also think that we're going to wrestle with how much granularity of data do we actually need. And I say that because I can almost see two different needs from a grid perspective. One is if you think about what is required on operations, real-time decisions, managing through multiple, status indicators and other things that help people who operate the grid make those decisions. So that's one level of granularity I think that needs to be carefully paid attention to, whether we need every customer to have that visibility, or what's the right level of aggregation, which I think helps us frame what the communication and security requirements would be. But the second thing that I think is an emerging and continually growing gap is the ability to forecast what the future demand is going to look like on the grid. So even if we think of simple things like the Internet of Things, not simple in a sense of you know, what that profile is going to change, simple in the sense that customers can have these options. But if you think about how you would forecast, say, you know, new development or what customers bring new demand to the system, how do you then take those methodologies that were created from the past, and how do they apply in a world where you do have the Internet of Things and the behavior of customers isn't as you know, historical performance is now always an indicator now of what the future is going to be. So I think, you know, that's really the distribution level granular forecast. But then how does that then mesh with the transmission system forecast needs, which is a much higher level of view of aggregate behavior that's a combination of all these different multiple things. So I see this kind of emerging problem with being able to decipher between what the gross load is on the system, separating, you know, organic growth from generation distributed energy resources, and really the net load. And I think in order for us to have the ability to optimize between the distribution and transmission systems, we got to figure out a way to sort of bridge that gap.
Thank you. Question?
Thanks. This is Gavin Purchase from the Environmental Defense Fund. My question is, from your presentations, it seems that one of the key aspects is location. Added to that is a temporal element. And what I mean by that is, if you were looking at, let's say, putting a distributed generation asset onto the distribution grid, you would be putting, you would ideally want to have a price signal that says it is going to be better to put it in this location where there is no grid constraint as opposed to this location where there is. Similarly, when it comes to pricing, you would like to be able to give a price signal to consumers to say, this is the ideal time for you to reduce your energy use, and this is the ideal time for you to increase it. Would you agree that location is essentially a component, an essential component part of moving this forward? And if so, how do we get there?
I'm happy to start. So the short answer is yes and no. Location is a mantra. We think it's only half the story. By all means, the grid has its current design. It's static today. And any engineer, you know, my boss, the engineer, would say, yep, an engineer would want to put DERs in 2 locations, where it's low cost or where there's high benefits. That's great, and we highly support that. The third piece, however, that's left out of that is customer choice and the fact that the grid can change. Hawaii is a great example, once again, to come back there. They did a great job of putting PV in places that had value and were low cost, had capacity. Hawaii ran out of that capacity. Now they're at a location where most of their feeders are maxed out, and they're sitting in a place where the utility didn't make the investments to actually increase the carrying capacity of those circuits. Had they accurately thought about how DER was going to grow, how customers wanted to install, and where they're going to install, they may have proactively started to invest in those circuits to increase that capacity. By all means, we support putting these assets where they're needed most. We support where they're putting them where they're cheapest. The third component that we think has to be absolutely part of the utility planning process is forecast where customers want to put them. There's an inherent right of customers to be able to manage their own energy, put in their own EVs, put in their own PV, and if you put an artificial block on that, you're living in a world where the grid is more static than it actually has to be on a timing, on a 20-year timing or planning schedule.
Yeah, I would say it slightly differently, but basically I'm in total agreement that it's location, but it's from whose perspective, right? So we have talked about, from an engineering perspective, if it's cost and reliability, that's fine, but we also need to listen to the customers. As far as considering other attributes in determining what is the best location. So that's one aspect of it. The other aspect of it is it needs to be looking at it from a scenario planning standpoint. That may be the right location for today, how would that change 5 years from now, 25 years from now? So which is the other aspect of it on short term versus long term.
And I'd answer it from the, also agreeing, but maybe answering just slightly differently. We've done some early work around looking at, say, a particular distributed generator as a grid asset, in a sense of, you know, its capability to defer some type of upgrade, whether it be on a feeder or a substation level. So we used to think things like, okay, well, if you put it on a certain portion of that feeder, you'd resolve its particular issue. What we quickly started to find out is that that's somewhat limited us in the sense that the feeder configurations, as soon as they changed, the problem shifted. And so we started to think about what's the right level of granularity in terms of when we talk about location. So if I'm going to defer a particular feeder or have a benefit for a feeder, whether it be voltage or capacity, that we might want to sort of look at a broader area around that feeder because of that reconfiguration ability, to take advantage of different capacities and adjoining capacities, and maybe you know, really look at what the grid reinforcement ought to look like in that world, as opposed to one-for-one replacement, upgrade for upgrade.
My only comment is, I think, back to the customer, if it's for energy only, it should be open access, right? We probably have that responsibility as a utility to develop a grid that if anybody wants to hook up, we hook them up, right? If you want those additional benefits, then it has to be in the right time, right place, and right size. Question?
Hi, Arthur O'Donnell, California Public Utilities Commission. I'd like to throw to this panel the issue that Peter Reed raised twice, because he thinks it's important, about having storage and PV export to the grid simultaneously. His contention appeared to me to be that, from an engineering perspective, that is actually an optimal use of the system, and yet we know that that is a big problem for utilities. And it becomes a big problem, especially for net energy metering devices. So I'd like to hear from you guys, because you are engineers, what is the problem? Is there a problem? What is the problem? How extensive is the problem? And how do we get past that?
Well, I'll start with that. I'm not sure if we know it's a big problem or not yet, right? We've only put a few of these systems out in the distribution system. I think, you know, on a bulk power system, it's less of a problem because things have this network type flow. But just in theory, if that works best from an economic point of view, we can make a system work like that, right? And I think, you know, we're looking at things like the duck curve that 5 years ago, we didn't even know what that was, right? I mean, we had peak times that are, you know, between 2 and 6, and now we're finding from an energy perspective is we have more energy than we need at that time. And we'd all like to go to a higher RPS, but that's sort of the constraint right now. So how do we use that in the middle of the day? And it's very possible that we'll be charging batteries as we're just, you know, as the solar PV is working. So I think that's a real scenario, and we just need to make sure our systems can handle that. But you think about the duck curve. If we ever want to go past 33%, we have to address the duck curve here in California.
Arthur, you may be surprised. I agree with my boss on this one. And I think what he was news to everybody. One of the challenges, I think, maybe is there's some artificial constraints on the operations of these systems right now. In many ways, I think those constraints will be alleviated and will grow. You know, one example is in a demand response setting. Right now, our distributed assets can only actually offset the current load that they have at that site. And I think Peter's comment was, well, you know, we could offset all that load, plus we've got extra capacity in that battery that we could deliver. And for us right now, I think there's some constraints to operating these assets that are not leveraging their full capability. And that was one example I think Peter called out.
Yeah, and I think similarly that I don't believe it is a major problem, particularly on a local basis. You know, as long as your transformers and your conductors aside accordingly, you can take the power. That should be no issue. I think the other consideration is on a total system standpoint, on a total T&D and generation systems perspective. Are you running into? Will we be running into problem because of too much generation? PG&E has a pump hydro plant that's more than 1,000 megawatt, and in the past we typically use pumping that plant at night. In the recent year actually started in 2013, we are pumping during the daytime, which is which is a huge change in terms of how the plant has been operating for the past, in its first 30 years versus what's been going on for the past 2 years.
And I think for me, it depends on what problem you're trying to solve, and how many of these devices do you have on a single location, what the size of those devices are, given the fact that we probably can't, every device isn't going to behave the same way all the time. So I think that there may be instances where you do need capacity, where that could support, not capacity, but you need to offset the amount of load that's there. But at the same time, if you had a large number of devices in a particular area, we'd have to really start thinking about the behavior of those devices in aggregate. And we're starting to believe that there's somewhat of a different profile that you would see just organically because the devices have this diversity amongst them in their operation. So to the degree that we understand those individually by location, I think will be important to decide whether this is a problem or not.
Okay, so we have consensus that this should not be a barrier toward interconnection.
Could we call out from the slide, you guys have been doing some tests in controlled settings, you might have something to observe.
Where's our microphone? Sorry. There you go. Sorry. Right over here. Sorry. I'm sorry. One of the issues that you actually are facing when you put those capacities or batteries or distributed generations on a meter, or at a localized circuits, one of the problems that you have is that when you actually exceed the load with that circuit, you create some local power quality issues. And in fact, we actually have a circuit that we started, say, this is great. We got plenty of industrial load here. We put in feed-in tariffs. And the next thing you know, the load that we had, the local generation, the customer said, hey, you know what, we want to put in CHP. And then another dairy digester said, hey, we're going to put in dairy digester. So all of a sudden, all the load that we have on the circuit all went away. But you still have customers actually connected to that circuit. So that means now you got to put investment in to resolve the power quality issues. So I absolutely agree, the panel here is that when you talk about locations, when you talk about capacities on those circuits, it is localized. And you do have to understand, besides just saying, well, globally, can the system actually take this much capacity and this much energy? What are the local power quality protections and operation issues that you're looking at? And are you putting artificial constraints in there? Or do you actually really have real constraints? And you do have to kind of run those scenario analysis and scenario planning so that you only put the constraint that you need to put in and then open it up to the market. So that is really one of the concerns it depends on who you talk to. Certain areas that we have in SMUD, no issues at all. Certain areas, like downtown network, we can't put any solar in because the equipments have a network protector. Anytime you see reverse power flow, you trip out downtown. Well, that's probably not going to be very acceptable. So you have to think about what is the engineering solutions that you want to open up, the integration of distributed generation, but yet not cause additional costs or additional operating efficiencies for the existing grid. And that's really what kind of the challenges I think everybody is trying to work, all engineering right now, is trying to put their heads together and said, how do you actually, optimize the benefits, but minimize the cost and the operation inefficiency that you have.
I think there's a question in the back there with the. Yep.
Focusing heavily on rooftop solar. The policy that's coming to California is community energy, and there's a real opportunity with community energy. And for example, cities like San Francisco that are very heavily renter-oriented, and a lot of commercial customers are renters, right? So if we're actually going to get to these higher levels of renewable energy, it seems that the location equation and the right size, right timing is a real opportunity for the utilities to work with developers on finding those right locations and potentially pairing up, for example, utility scale storage along with those correct locations. They're still close to the off-taker or close to the subscriber. And orchestrating those types of programs, I'm wondering how the players will work together when we've got focused so much on rooftop solar. How do you see that evolving as community
So maybe just to add a little bit to that, in the context of the distribution resource plans that are part of AB 327, how do you see that sort of engagement or an opportunity as those plans get developed and stakeholders are engaged? So maybe a couple of you want to touch on that.
Yeah, I'll address really quickly. I mean, in general, Solar City is supportive of more solar and a distributed grid. So community solar is a great thing on our eyes, particularly since it has the capability to open up access to solar to folks that currently don't have access to it. Renters typically, or people that don't meet the threshold of financeability. And that's probably been one of the main constraints for the industry in general, is how do you finance this with different FICO scores and things like that. And then maybe to reference Paul's topic really quickly, one exciting thing coming out of these DRPs is the identification of location, or identifying locations where you could put these assets. And when those assets are not served by the market, let's say it's in a highly multi-tenant location with renters, I mean, we're as supportive as the next person to say, yeah, community solar might be great.
Yeah, and we, from San Diego, we have an application in front of the commission now to have a community solar type program where if a person didn't have a roof to put solar on, that they could actually buy into that. So we think that's a big piece. And then the battery piece, that's really where we see this going. We think it's going to be a combination, just like the storage procedure, it's going to be transmission, distribution, and customer side storage. So we think having storage on the distribution system will and is part of our planning going forward, and it really is going to be essential to how we actually manage those three pieces, right? But having storage on a distribution system that can actually improve our utilization and improve from our service from a reliability point of view to customers, we're all in favor of that.
So we're going to wrap up here, and but I would like to ask one last question in closing. We have a number of people participating today that are from different parts of the country, looking at these same sort of set of questions and issues that we're discussing in the More Than Smart scope. And so maybe if I might ask each of the panelists to touch on what you think are the key learnings through the process that's been going on in California over the last year or so, and particularly with the More Than Smart effort, that you think might be useful for other states to consider or to understand. So maybe Brian?
Yeah, sure. My learnings are on process entirely. I think that the process of the regulator support of collaboration in order to drive progress on these very challenging topics is incredibly valuable takeaway from the More Than Smart proceeding. You also see it in the Smart Inverter Working Group. These are discussions that are very technical, and there's not a clear answer. Sometimes it's not the best avenue to discuss it in a proceedings per se. It takes a lot of collaborative engagement. I think there's been a lot of success with that.
So one of the key learning for the engineers at PG&E is listen to the customers. In essence, we can solve another problem, but we need to make sure that we're solving the problem to the benefit of the customers.
And from my perspective, I think we're looking at a lot of technology here in California. The work we've done with smart inverters is definitely something to follow. We have some really solid microgrid pilots out there. We have one in San Diego. So all that technical things have to come together, but I sort of agree it's about the customer, and I think being able to have a forum like this where we have policymakers, regulators, customer representatives, and utilities, this is the way we'll make progress going forward in the future.
Yeah, and for me, the More Than Smart effort was really informative for me, getting folks that you normally don't deal with on a day-to-day basis to understand what the concerns, what they see sort of the future unfolding, and really the convergence of those ideas. It's interesting to me that I haven't seen a lot of big gaps between where people thought the grid ought to go, where technology ought to go, what customers should benefit from. So I think that sort of collaboration can be carried over in different forms.
Well, please join me in thanking the panelists for